Hello, my name is Shahzad Ali, and this is my machine learning project. My background is in cybersecurity, and the problem I'm addressing is one that almost every large organization faces today. How do you know whether the human, non-human, service account, or AI agent accessing your most critical systems right now are actually supposed to be there? Today's privileged access management or PAM tools rely heavily on static rules, roles, IP allow lists, and fixed time windows. Those rules work for basic account and access control, but they completely lack context. Over the next 10 minutes, I will walk through why this is a strong opportunity for machine learning, how I frame the business problem using CRISP DM, how I would validate the solution with real users, the core ML system design decisions, and the key risks I anticipate in production. Okay, so I will start with the opportunity evaluation. A large percentage of machine learning projects fail because teams choose problems that aren't well suited for ML. To avoid that trap, I evaluated this idea using the three criteria from the course. Number one, is there a real problem? Number two, can ML solve it better than alternatives? And number three, and does solving it actually matter or help solve some pain points? First, is there a real problem? And the answer is yes. The legacy PAM systems make binary decisions based on static permissions. If an account has access, the systems says, yes, you can access this system, let's say AWS or a virtual machine, a database, and whatnot, even if the behavior is completely abnormal. In practice, this leads to two outcomes. One, analysts are flooded with noisy alert, or worse, the real attack slipped through undetected. So my conversation with SOC analysts, IAM administrators, identity and access management engineers, and security leaders consistently confirm this pain point, and the financial impact of breaches makes it a serious business issue. Second, can machine learning solve this better? The answer again is yes. Why? Because the access risk is inherently high dimensional or multi-dimensional. Whether a login is risky depends on time of the day, location, velocity, peer behavior, device posture, identity, and many other signals taken together. Rules cannot capture these interactions, but ML models can learn behavioral baselines per identity and detect meaningful deviations in real time. The good news is, and the important thing, that the training data already exists in enterprise access logs today. All right, to point number three. This problem sits squarely in the high feasibility, high impact quadrant. Solving it reduces breach risk, improves analysts' efficiency, supports compliance, and uniquely enables a secure use of autonomous AI agents. And we know that agentic AI, the AI, Gen AI, they have been adopted by large and medium-sized enterprises across the board. So definitely that makes it a compelling opportunity. Okay, let's talk about the CRISP DM business understanding. So using the CRISP DM framework, I define the business problem clearly. The primary users are SOC analysts, compliance engineers, auditors, IAM administrators, and CISOs. At mid to large enterprises, managing both human users, non-human users, and a growing number of AI agents. The core problem is that static access policies create friction for legit users while failing to continuously access risk. Okay, so access is granted once without ongoing evaluation. So you are in the session, you got the access, there is no mid-session evaluation happening with the legacy tools. So, and your context is also ignored. This becomes especially problematic for AI agents. These non-human identities don't follow predictable scheduler or location. They have their own brain, they can make their own decisions, and they can deviate from your normal automation or orchestration path. So the existing PAM tools were never designed to model their behavior. What about success metrics? So it's defined using both outcome and output metrics. So on the outcome side, we want a measurable reduction in unauthorized access and a reduction in analyst time or auditor time spent on false alerts. On the output side, key metrics include keeping false negative below 2%, false positive under 5%, decision latency below 200 milliseconds, strong AUC ROC performance, and reduction of mean time to revoke access. And this data or metrics are collected based on the industry standards and what others have accepted as part of the guidelines, compliance guidelines. So the key feature include the temporal pattern, geolocation and IP repetition, request velocity, resource sensitivity, peer group deviation, and the API call sequence triggered by the AI agent. Now, device or identity fingerprint is also very important, and the approval change management ticketing is also taken into considerations. There could be many factors here, but I'm keeping it to these you see on the screen. And we can change it, we can adopt it during our testing phase. We can see if these are making sense or not. If not, we will change it or make adjustment to this. So let's quickly talk about the validation plan. So rather than assuming the solution is correct, I validate it through iterative experiments with real users before committing to full development. The core concept being validated is a system that builds a rolling behavioral baseline for each identity, scores every access request in real time, and applies a tiered response from auto allow to step up authentication to denial and analyst alerting. The first experiment is problem confirmation interviews with the SOC analysts and IAM admins to ensure alert fatigue and mixed threats are truly the dominant pain point. The second experiment uses simple wireframe to test whether user intuitively understand risk scores and workflows. The third experiment introduces an interactive prototype with the historical events to measure decisions speed and accuracy. And finally, a shadow mode pilot runs the model in read-only mode to collect real-world feedback before any enforcement is enabled. So these are different experiments, or you can also call them GATE. ML system design. So at the system level, access logs from enterprise systems feed into a unified feature store that maintains rolling behavioral baseline. An Ansible model primarily XGBoost with sharp explanation supported by an LSTM for sequence analysis. It produces a calibrated risk score from 0 to 100. That score drives a tiered response. There are three key decisions in terms of designing it. First is a hybrid learning strategy. So weekly batch retraining to capture long-term trends combined with daily updates to per identity baseline so that the system adapts quickly to legitimate changes. The second is tiered human in the loop model. Very low and very high risky decisions are automated to meet latency requirements, while human focus on the ambiguous middle where judgment adds the most value. The third is interpretability. So the security teams and auditors requires explanation. So that's the reason we have XGBoost with SHAP as our primary model to handle that. The LSTM detects complex sequence anomalies, especially for AI agents, while the interpretable model explains the decisions to human in their human natural language format. Finally, I considered production risks. Data drift can occur, as we know, when organizational changes shift access patterns, leading to false positive. For example, the mergers and acquisitions. This is mitigated with drift monitoring and automated retraining. Concept drift is more dangerous. That's the reason you see high here. Attackers may slowly mimic normal behavior before escalating, or AI agent updates may abruptly change behavior. These are mitigated through peer group analysis, model ensembles across time windows, and explicit agent version signaling. Additional risks include training, service, skew addressing through a unified feature store, and feedback loop corruption. This is mitigated by maintaining a clean, analyst-curated evaluation dataset. To close, this ML-based privileged access management system addresses a fundamental gap in enterprise security. Static rules in a dynamic world, they cannot exist. The opportunity is real. Machine learning provides a clear advantage, and the business impact is high. The project demonstrates a complete AI product framework from opportunity evaluation to crisp DM business understanding to user validation, system design, and production risk planning. As organizations adopt autonomous AI agents, access management must become intelligent, adaptive, and context aware. The static rules were built for a static world, and that world no longer exists. Thank you.